It's a little bit more. It goes like server, but. Which day? Oh, what? There's another one?
Schweiz, that's beyond my. Is
that what the sign is? Yeah, the sign for the dormer.
Okay, we're going to get started in a moment, but first I just want to make a couple of announcements. So it's been a long month. I understand it's been a long month, and I know it's hard to keep yourself motivated to come into lectures. And all of you that are here now, thank you for being here. All of you that have friends who are not here, put pressure on them to come tomorrow. Okay. And yeah, so let's try to finish with high attendance on the last day. That's our great memory. And also we're going to have a discussion at the end of the day about the school overall. And I think the more people that come to that, the better. I understand that many of you have flights tomorrow afternoon and you can't make it in the afternoon. Of course, that's fine. But otherwise, if you're in Boulder, please be here tomorrow. And to sort of that was my, that's my plea. And to help facilitate higher attendance, we're going to start 30 minutes later tomorrow. I know that's not like a huge thing, but it will be easier to roll out of bed after a nice night 30 minutes later than otherwise. Sorry, I don't.
Oh. You say you should still tell people.
Oh, that it's 9 o'clock.
It's still 9 o'clock.
But there are, and maybe you're not one of those people. There are a lot of people here that show up at 9, and I say thank you very much. And so yeah, I don't want to leave those people in a lurch. So, but a great joke nonetheless. So anyway, the last thing to point out is that our lecturers are going to be sticking around after lecture today. Everyone who's here is promised to stick around for at least half an hour after Ty's lecture. If you want to ask them either about the problems that they assigned this week or just about anything, about their research.
Life, the universe, marriage.
Everything. So without further ado, that's the perfect segue to a tie.
All right. Okay. So I'm going to give the third lecture on this idea of how to design machines and materials. And we talked about designing machines around cusps and how to think about designing machines at the micro scale. And then 2 days ago, we talked about this challenge of printing a 3D organ that has mechanical properties. And again, this idea that by organizing the network around a mechanical phase transition, the rigidity percolation transition, you could really have a lot of flexibility for the cells that are in the tissue that are modulating its properties over the long term to modify its behavior. Okay, and what I want to do today is I want to talk about how we can do that with materials in the lab. All right, so I want to talk about what we're calling viscosity metamaterials. And I start with this beautiful image of a pile of sand that has both of the properties that we're interested in. One is this solid property that the heap has when it's resting in your palm. And the other is the fluid property of the sand grains that have already flown through the fingers. And to kind of help motivate, the really broad range that these properties can have, I want to show you this video by Mark Rober. And so Mark is one of the great science popularizers, and he excels at building machines. So let me play the video, and we'll go from there. Oops. So I got to do this, I got to escape, and I got to play.
Filled to the brim with solid sand. This is one of the coolest things ever. If you take a tub of sand like this, and then add air in just the right way, it basically becomes a liquefied soup.
Okay, so I'm going to stop it here. This video probably evokes fond memories in Doug, who actually started his career investigating these fluidized beds. And these fluidized beds are super important in industry. Whenever you want to transport particulate matter, you fluidize it. It makes it very easy to move from one place to the other. But one thing that's really difficult to control in these fluidized beds is there aren't really many in-between states. You're either fluidized or you're a solid. And in the solid state, you have all these force chains formed between the grains that are keeping the material from flowing at all. And one of the papers that really inspired me was by one of our other speakers, Andrea and Sid, who pointed out that if you take these kinds of jammed systems, these systems that are being held solid by these disorganized force chains, and you start doing something called tuning by pruning, which I think you talked about in the earlier lecture, you can actually change the properties of the material by many, many orders of magnitude. And so here on the right, we're looking at the ratio of the shear modulus to the bulk modulus, and you can see that even though you may start at one particular point, by optimizing for different for trying to optimize either the shear or the bulk modulus, you can get this ratio, okay, to be very, very different, 13 or 16 orders of magnitude different between the data points here and here, okay? And this really is where the promise, in some sense, of granular materials and disordered materials is, that you should be able to change the properties by many, many orders of magnitude if you could figure out just how to organize those grains, right? And in that sense, it's something that still remains as an open holy grail in the field. How do we invent a process similar to something like cold rolling in solids, in crystalline solids, where we can manipulate those bonds and essentially tune and prune the system so that it gets into a state with the properties, the desired properties that we want. And if that promise is reached, then we could take any pile and essentially get it to the properties that we want with a huge range of possibilities. Okay, so that's kind of the idea. And what I'm going to try to say is that I think we can get there if we start thinking about fluids a little bit differently, if we start thinking about them as metamaterials. And so in the world of metamaterials, the idea is that you create materials where there's some medium length scale that you've structured the material on. And so if you, for example, have little oscillators and capacitors that allow you to induce capacitive and inductive fields, and you place them in particular ways, you can create a cloak, which is what this metamaterial is. You can punch holes in a sheet of rubber and create a material that has a positive or negative Poisson ratio, or something that is anywhere in between. And you can do this at the microscale as well by patterning lattices that can change their conformation from rectangular, or when they expand, to something that's buckled. Okay, so all of these are examples of metamaterials, and the question is whether or not we can do that with fluids, all right? And so I want to tell you about at least one system that we've been studying. I don't think it's the only system you can do this in, but it's a fun one. It's oobleck, cornstarch, and water. And the idea here is that this material is kind of in the in-between the solid and the fluid phase, okay? So by putting a fluid along with the grains, you're able to create something that on a long time scale flows like a liquid, on a short time scale is solid enough to support the weight of a human being walking on top of it, right? And I think these materials are nice because unlike fluidized beds that can either be fluid or solid, here you can have something that's in between, and that gives us more room in order to design our metamaterial. You should not think of it like a glass. We'll talk about what it is, but it's not a continuous phase transition. Well, it's not a glassy phase transition. It's a continuous phase transition, a second order phase transition associated with jamming and shear jamming. So we'll talk about that. Okay, so let me give you the idea behind shear thickening fluids, and I'll give you a little bit of a history just so that you're brought up to speed. But I will quickly try to aim this at our current understanding rather than dragging you through all of it. Okay, so the idea behind shear thickening materials is that if you plot the viscosity divided by the solvent viscosity versus shear rate, then at low shear rate, you get one value for the viscosity, and at high shear rate, the material thickens and you get a different value for the viscosity. Okay, and the way this works is that if you think about, and this, by the way, can be orders of magnitude change in the viscosity, okay? It can be a really stark change between the Newtonian and thickened states. And the way that you want to think about it is that viscosity is really the ratio between the stress and the shear rate. Okay, so if I plot the stress and the shear rate for some liquid, it'll have a linear relationship. The slope of that is the viscosity. And the idea that Cates and Weyer proposed was that this relationship between stress and shear rate really depends on the configuration of the particles. Okay, so it might be that if you have one configuration of the particles, you'll have one relationship between the stress and the shear rate. Whereas if you have a different relationship between the particles, a different structure or a different set of interactions, you might have a different curve associated with that. That'll give you a different viscosity. And if that transition occurs over a range of stresses, then you can get shear thickening as the system transitions from one stress versus strain rate relationship to the other. Yes? So if you have a relationship that is like this, where all of a sudden when you jump, okay, the transition point is behind you, then you get discontinuous shear thickening. Okay, so that's where you get jumps in the viscosity, and it is indeed double valued, and this is where you get the hysteresis for the transition. Okay? All right. So for many years, the field was plagued with this problem, which was, what is really the difference between these kinds of configurations? All right, and we did some early work on this. This is work by Xiang Cheng, who's now at the University of Minnesota in the chemical engineering department, where we saw these clusters in moderately thickening suspensions. And we thought that this was evidence for something called hydroclusters. So that was an idea that was there for a long time. But very quickly, and really championed by John Brady and Norm Wagner, but very quickly, we started learning as a field that there are most likely frictional interactions that are governing the differences between these kinds of particle configurations. Okay, and this is work that was originally done by Lutens, who's now a cement engineer, but really brought into the field, I think, back forcefully by Heinrich Jaeger and Eric Brown. Okay, and so the idea that we wanted to check was which theory was right. So we had a little bit of a role to play here. Is it really due to hydrodynamics, or is it due to contacts between the particles? And people were also worried about Brownian stresses. So I'll just give you like the basic idea, which is that if you have hydrodynamics for low Reynolds number fluids, if I take two particles and I try to move them close to each other, okay, so that they're squeezing fluid out, that force is going to be identical to the force pulling them together if I pull them apart. Okay, so the forces have to be symmetric backwards and forwards. That's because of the time reversibility of the Stokes equation. Whereas if I have two particles that are in contact with one another, in one case, when I push, you're really pushing against the elastic modulus of the particle. When you release them, there's nothing that's pulling them back. Okay, so contact has a fundamental different relationship. This was pointed out by Andy Akravos way back in the day. And we did this experiment for shear thickening systems that I think was kind of helped clarify that. So the idea was that you're going to put a strain, like a shear rate, and then you're going to reverse that shear rate, okay, in this kind of triangular wave. That means that your shear rate is going from a positive value to a negative value. You measure the stress in your rheometer, and from that stress, you can back out the viscosity. And the idea is that if really things are hydrodynamic, then you should see the same viscosity on the way forward and back. If things are due to contact interactions, then you should see a drop in the viscosity, all right? And so I'm going to focus on just one of these quartiles, okay, so just one experiment, right after we do a shear reversal. And so the idea is you get your system into a viscous state, or rather that you do this shear reversal at different points along the shear thickening curve, okay? So you go to here, the system is not shear thickening at this shear rate, and you do a shear reversal experiment, and you get this curve over here, okay? And reversal happens at 0. If you go to a slightly thickened state, okay, over here, what you see is that the system comes back to this initial hydrodynamic level, and then you get a little bit of an increase here by the time it finishes straight with the high shear rate. Okay, so transitions to a thickened state, and so on and so forth, so that by the time you get to over here, what you see is that that thickening is really coming not from the hydrodynamic part, which is explained by this portion over here, but rather by the change in the viscosity due to the contacts that are forming once you reverse. Is that clear? Okay, so that's what a shear reversal experiment gives you. Really, this was done by Neil Lin, now at UCLA. And when we first did this experiment, we got a lot of flack from people like, you know, is this really contact, or is this, you know, like something, you know, that's like not really contact, or, you know, what exactly is going on at the particle surface? How do you get, you know, like frictional interactions, blah, blah, blah. And so I want to just take a moment to give you my view of repulsion, contact, friction, and all that. And the basic idea is that, you know, you can take a bunch of bowling balls and you can stack them. And, you know, I think we could all agree that that's contact. Okay, an engineer would say that's contact, a physicist would say that's contact, particles touching each other is contact. But when you're talking about particles at the microscale, you can also have things like charged double layers, and those charged double layers could lead to short-range repulsions between the particles. And so in that system, you would also effectively see contact. In fact, what is contact but electric repulsion at the atomic scale? Okay, and if we have it at a slightly larger scale, I don't care. It's still effectively contact. Okay, what I call moral contact. Okay, so like the best way I can say it is that like if you're a literal person, like an engineer who's like literal, this might mean contact. But if you're a physicist like us, this is close enough and it's still contact. Okay, and you can do the same kind of analogy for things like friction. And indeed, when you start, you know, as the field is developed, there have been many, many contributions to show that you can get shear thickening that arises from roughness of the particles, okay? So real undulations, now not at the molecular scale, but at the roughness scale of the particle. You can have particle shape affecting when the onset of contact occurs. You can have things like surfactants that can modify those contact interactions. Hydrogen bonding can lead to higher effective friction, and so on and so forth, okay? And what I'm going to do is I'm going to try to sweep all that under the rug. I'm going to throw all that into my physicist funnel, and I'm going to say that all of these things are just various ways, a zoo of ways to create an effective constraint against sliding, okay? And so really, when you're thinking about shear thickening, or any of these kinds of interactions from a physicist's point of view, if you want to focus on larger scale phenomena than what's going on at the particle scale, really you're asking, can the particles penetrate one another? Can they slide relative to one another? Can they twist? Can they roll? Those are the constraints that we're talking about. And the idea here, the effective idea that Wiart and Cates pointed out, is that when you go from one curve that describes the viscosity to another, really you're changing the constraints. Okay, so let me show you how this goes. If I'm over here, this is the volume fraction phi, and I'm plotting the viscosity as a function of volume fraction, at somewhere around 64% is the random close packing limit for spheres. Okay, so if you have anything that is at random close packing, it is jammed. There is no way for it to flow. The viscosity is infinite. But I can also create a packing that's stable at a lower volume fraction if the particles have a constraint of no sliding. Okay, so if I have friction, then I end up getting a random loose packing. And now the viscosity is going to diverge somewhere over here at a lower volume fraction. So if, as a function of that stress, as I shear the system higher and higher, particles are coming into contact and experiencing frictional forces that prevent them from sliding, then essentially over that stress range, I can go from a constitutive relation associated with the blue curve to one associated with the red curve. So if I started here, then I end up over here, my viscosity has become larger. That's shear thickening. If I start over here, where there are no solutions in the red, I can get shear jamming. Is it clear? Yeah. Go ahead. No, so the idea is that I'm not going to care about the origin of where friction comes or where contact comes. Let's like fuzz our eyes and not care. So when you go from systems that are in contact with one another, okay, the most that you can pack them is random close packing. Okay, at that point, the viscosity is going to diverge. If I have particles that have friction between them, in addition to contact, in addition to repulsion from overlapping, then I can generate a random loose packing. It's why, I think I have it here. Yeah, so if I pour my cornstarch into a graduated cylinder, actually this is Anna who poured the cornstarch into a graduated cylinder, and we mark the line where the cornstarch is with this red over here, and then we're gonna Anna's gonna tap the cylinder. So here we go. You can see that the powder shrinks down. Anna's really fit. She's like a professional chef. See that the line is now well below the red. And that's the point, that when you first poured it in, that packing was stabilized by friction. And as you vibrated the system, those frictional interactions were like released and the system could densify. And so the difference between those two is what causes shear thickening. That's the Wiart and Cates model, okay? And what I'm going to try to convince you of is that that whole framework can be recast into crossover scaling between critical points. Yeah. There's cornstarch particles, those are granular, and there's a fluid between them like glycerin or some water or something. If the particles don't touch, then they can move past each other, they can move through the fluid. If the particles touch, then there's frictional interactions between them, and then the system shear thickens. Yeah, so when you're so what the tapping is telling you, okay, is how to release the frictional interactions. I haven't shown you how we do that in the experiments yet. All I've said is, in the experiments, you start off with something that can easily move, but when you shear, it gets into the frictional regime, where now it can support stresses at a lower volume fraction. So effectively, the system is closer to the rigidity transition, and its viscosity increases. Yes.
Shear jamming, random packing.
Yeah, so random loose packing is this, okay? Random close packing is this. Shear jamming, I'll talk to you in a second about, but it's the idea that when you shear the system, it completely jams. And the way you can see that in this curve is that if I go with this blue curve, okay, and I start off with everything being able to move past everything else, and then I start to increase the frictional interactions so that all of a sudden the maximum viscosity is over here, denoted by this dashed red line. Let me put my, denoted by this dashed red line. Then all of a sudden, if I increase the frictional interactions, there's nowhere to go to. There's nothing. Okay, the system becomes jammed. So on the right side of this red line, with frictional interactions, the system is jammed. On the right side of this blue line, without frictional interactions, the system is still jammed. Okay. Yes. So far, so good? Other questions? Okay, so what Weird and Cates says, okay, their model is that you have this divergence of the viscosity, and the way that the viscosity diverges is the same way that it does for jamming. You have some jamming volume fraction, and it goes like the distance between the volume fraction and that jamming volume fraction to the power -2. So as this goes closer and closer to phi j, you get a divergence of viscosity that has a square-like dependence. And what they said is that this phi j is no longer going to be just a constant. It's no longer just going to be the jamming volume fraction for isotropic frictionless particles. Now we're going to allow it to float. And the way we're going to allow it to float is with this function f of sigma. F of sigma is the fraction of frictional interactions. And so as I increase sigma, it goes from something like when you have this is 0, this is e to the minus infinity, so it's 0. When I increase sigma, this goes to 1, okay? Right, as this goes to e to the 0. And this threshold occurs at sigma star. And so what happens is if f of sigma is 0, this term goes away, this term goes away, you're just left with the jamming volume fraction at random close packing. But if f of sigma is 1, this term goes away, and then your volume fraction is now the shear jamming volume fraction, or the loose packing, random loose packing volume fraction. Okay, so that's how this works. Okay, and the way you construct the phase diagram for this, so again, if I plot the stress on the vertical axis and the volume fraction on the horizontal axis, this is the jamming point. If I go beyond this, then I get the system is jammed just because I cannot fit any more particles in there, okay, even without friction. But as I increase the stress, I'm moving from this blue curve to this red one. So this right here denotes the limit. This is the random loose packing limit, okay, this line right over here. And if I start over here on the blue curve and I go up, I'm going to reach a shear jammed state. All right, and that's really what I want you to get out of this. The blue and the purple regions are the continuous and discontinuous shear thickening regimes, but let's ignore that. I just want you to focus on the jammed and the shear jammed regimes. Yeah. They're similar. The system does not flow. It's rigid. But whether or not there is a difference is an interesting question. Like, are all rigid systems the same? And what Andrea and sort of the whole tuning by pruning showed is that actually they could be quite different. And so I'm going to show you how to start manipulating these phase boundaries in order to access those things. Great questions. So far, so good? All right. Should I pause? Okay, let's see if let's see how we do. Okay, so the question is, are we done? So Weird and Cates wrote this beautiful theory, this beautiful model, And I would say that it's still not exactly a theory of shear thickening. And what I mean by that is that, for the jamming point, there's been a lot of work over the last couple of decades, again, really spurred on by Andrea and Sid's ideas about this point and the fact that it's an out of equilibrium critical point associated with the packings of these particles. So this really, there's a lot of machinery associated with critical points that we've been developing over the last 50 years in the physics community, studying, these continuous phase transitions, especially with the renormalization group approaches that Ken Wilson developed. And the question is whether or not we can think about these other regimes also in the context of critical phenomena. And in particular, can we treat this upper point over here, okay, as another critical point? And if we can, does it have the same universality class? Can we, does it have the same physics governing it? In the Wiart and Cates model, the assumption is that it is the same universality class. There's a -2 here that is independent, right? The shape of this curve is the same as the shape of this curve. It just diverges at a different point. So I want to start to think about how we investigate this question. And the way we do this with continuous phase transitions is we use a scaling analysis to back out those critical exponents. So I'm going to show you how we do a scaling analysis in the shear thickening problem, and then I'll show you how we use our results to do interesting things. So I'm going to recast this. I'm going to take the phi j that Wiart and Cates wrote, and I'm going to plug it in to my formula for the viscosity. Okay, so all I've done is I've taken phi of j, which is this part over here, and I've plugged it in to the formula for the viscosity. I get this. If I now extract the divergence that happens for jamming of frictionless isotropic particles, okay, I can take that over to the other side. This is that phi naught minus phi to the -2, if it was on the other side, divergence that's associated with just packing of particles. On what's left is some function of the parameters, the combined parameter, f of sigma divided by phi naught minus phi. And if you want to know what that function is, this is what it is. So if you plug this into here, let you do that as homework, and bring the phi naught minus phi squared over, you'd get this exact formula. Okay, and what this function does is it says that when f of sigma, when the fraction of frictional contacts is small, when this is 0, okay, this term goes away, and this just becomes a constant. But when the fraction of frictional contacts is 1, then this thing will have a divergence when phi is equal to phi mu. And that's the divergence with the frictional interactions, the shear jamming, and they predict that it has the same power of -2. Okay, so what we can do is we can plot the viscosity times this function, phi naught minus phi squared, versus this parameter, the scaling parameter, f of sigma over phi naught minus phi, for real data. And if everything works out, then I should be able to collapse everything for different values of sigma and different volume fractions onto a universal curve, f. Is it clear? All right, so let's see how that goes. So here's data for cornstarch. Here's data for silica, two very different systems. Cornstarch is ugly grains and silica are beautiful spheres. You look at the Wiart and Cates collapse, and it's pretty good. Okay, it's not perfect. If I do it for the silica, it's not perfect, but it's not bad. Okay, it tells you that you're on the right trajectory. So how do we fix it? So it turns out it's not very hard to fix. So here is a scaling curve for both cornstarch and silica on the same master curve. And the only thing that we had to do to the Wiart and Cates universal function is to add this parameter C of phi. Okay, and I'll tell you what that does in a second. But really, this curve represents all of that shear thickening data for these kinds of particles, like very different particles. All right, it all collapses onto the same universal curve. Okay? this part over here, this part where this is flat, tells you that the fact that this collapses tells you that you have this collapse for the random close packing, right? And this part over here, where it collapses in the high X regime, the high parameter regime, that tells you that you have a universal divergence, a new divergence that's associated with the shear jamming critical point. And you can do things to test for the properties of the divergence. So first, let me tell you what the parameters C of phi and F of sigma look like. So if I look at these curves, they kind of look like F of sigma, but they're multiplied by C of phi. And what this tells you is that actually not all the frictional contacts in your suspension are going to affect the viscosity that you're measuring from your shear. Some frictional interactions are pointed in the wrong direction. Some frictional interactions are not associated with some network and therefore don't contribute as much. And the amount that they contribute actually is not monotonic with the volume fraction. So we see that for low volume fractions, you don't get as much of your F of sigma. And for very high volume fractions, you don't get as much of your F of sigma contribution. But for somewhere intermediate, that's where you maximize your F of sigmas. That's where most of the frictional interactions are counteracting the flow to give you your high viscosity. Okay, so if you have a very dense suspension and you shear it, many of the frictional interactions will be pointed in the wrong direction. Okay, so that's why it's low at this end. If you have a very dilute suspension, maybe you don't have enough contacts between the network to really align everything and get it to oppose the viscosity. So we don't know what the origin of this is, but this is the non-monotonic relationship that we measure.
And here you assume the wire indicates friction function, but allows C of phi.
To modify it. And once we do that, then we can get something called, we can get very beautiful scaling. This is another way to plot the universal function, that f of x, and the script f, the universal function. It's called Carty scaling. And the idea here is that when you plot it in this way as a function of 1 over x c minus 1 over x, this part right here tells you the power law associated with the frictionless isotropic jamming. And the fact that this part over here has a different slope tells you that the new divergence in your script f has a different power law. Okay, so this thing is transitioning from a power law that's really associated with frictionless isotropic jamming, -2, to a new power law. And the exact value of that power law is a little bit tough to nail down, but you can see that there's a clear bend in the data. The slope changes. Yeah. X is your scaling variable. It's all of this stuff, this jazz. Okay, so you're plotting script f versus x. And there's a new divergence at some xc, okay? And that's what you're seeing. Yeah. Yeah. It happens right there. Oh, well, that's the point of scaling analyses. It's not just one value of the volume fraction. It's not just one value of the stress. In fact, it's this combination of parameters that gives you that crossover point, okay? So I could have a high stress, but a low volume fraction system, or a low stress, high volume fraction system, and both of them could be at exactly the same point on that knee. And that's also the power of scaling analyses, is that instead of just trying to fit power laws to an individual data set, you're collapsing multiple data sets onto a single point in order to constrain the fit. Okay, so that's the beauty behind scaling analyses and why they're so powerful, and why when you get a scaling analysis, you feel like you're on to something really deep about the relationship between the parameters that are causing it. Yeah. For any curve you obtain, you will have values of the stress that you're imposing and the volume fraction, and it should collapse onto this curve if you plot it in the right way. Is that what you mean? You don't design the CFI. Each system has its own CFI curve. So in this particular case, I'm showing you for cornstarch, it's this one. For the silica particles, it's this one. We don't get to do anything about that. Maybe we can design it by changing the properties of the particles, how easily they slide, surfactants, hydrogen bonds, the details that I've swept under the rug. But once you account for that CFI, they all collapse onto the same universal function. So once I measure those CFI, I can tell you how to combine the stress and the volume fraction in order to get the systems to do the same thing. Yeah. I don't know enough about RG calculations to understand exactly what you're saying, but let me sort of say that our prediction is that this would be the RG flow diagram. It would be very similar to something like the Heisenberg to Ising transition, the crossover scaling between Heisenberg and Ising magnets. So in Heisenberg, again, you have isotropic alignment of your magnetization. In Ising, you break symmetry in the Hamiltonian. So instead, we're going to replace the Heisenberg with the isotropic jamming fixed point. You're going to replace the Ising with the shear jamming fixed point, okay? And you're going to get flow of the Hamiltonian from this one to this one, okay? Yes. Well, it's fictional, as in this is the flow diagram that we expect to get, but we are plotting real parameters here, okay? For this G function is just CFI times F of sigma. This is real. This dashed line, for example, that is determined from where the knee is. Okay, so this is data. Okay, this is data driven, but we don't know exactly, for example, what this, there has to be a flow into and out of this fixed point. We don't know what this boundary is doing. No, we do. This is our conjecture. It's not a full-blown RG theory. Yes, so X, you have this script F, okay, is a function of X, and X is equal to CFI times F of sigma times phi minus phi naught, okay? That's X. So that's my scaling parameter. I got this wrong. Yes. Correct. Yes. So I don't know how to answer his question about homogeneity. Do you have insights on that? It is. CFI has a different function for each material. Oh, because the point is that you just measure CFI once, okay? And then for any stress, you can back it out, right? So like it's just like, it's like sigma star is different for every material, okay? The onset of where that transition happens is different for every material. No, the functional form of F of sigma, once you account for CFI, the functional form of F, this script F of X, is exactly the same. Little f is, we use the Weart-Cates. Okay, that's little f. So you have to fit sigma star for each material. Yeah? Yes. Yes. Yes.
But CFI is a different function for each?
CFI is a different function for each material. So here's my function for cornstarch. Here's my function for silica. And you might be worried that we have like way too many fitting parameters, but the number of fitting parameters is much, much smaller than the number of data points and curves that we have here. Like you cannot do this. Like if you have a function for CFI, that's effectively like 2 parameters. You can create like a hill function if you want, like some sort of mountain function. Yeah. No. So we're doing crossover scaling. That's a little bit different. So we have 2 critical points that we're transitioning between. Okay. And the critical points, okay, are associated with the collapse on this side and the collapse on this side. This side, this is where the script F is constant. Okay. And that collapse comes from jamming, frictionless isotropic jamming. This divergence is associated with shear jamming. This function tells you how to go between the 2. Yeah. No, yeah, the CFI is independent of where you are on this curve. It's the same for that material. I can have a CFI, okay, that's over here, but if the stress is low, then I'm way over here on this curve. Or I can make the stress high, in which case I'm way over here. For each material, you need to make a measurement. Once you do, it collapses onto this universal function. By universal, I mean that I took all of those curves and collapsed them onto a single universal function. I feel like I'm still losing people, so I'm not sure where I'm losing people. We don't know, but I think what CFI tells you, it modifies your fraction of frictional contacts. Okay, so it's this thing over here. And what it tells you is that you start off with no frictional contacts, and you go to some number of frictional contacts that's some fraction of F of sigma. And it depends, and I think what it means is that not all of your frictional contacts are contributing to the viscosity. Okay, so there's some, something that tells you that for each volume fraction, that fraction is different. But once you account for that, all the data for that volume fraction, all the different stresses, all collapse onto that same universal function. So it's still a very powerful collapse. It's not like I have enough parameters for each data point to do whatever I want. Okay, it's a very constrained collapse.
But still weaker than universality.
No, I don't think so. I don't think it's any weaker than anything else in other materials. Okay.
And then I still don't understand the question back. Like if I measure some, approach to a critical point in one material and divide that function by itself, measure it, then I get 1, right? I get a constant function. If I do the same thing for another material, I still get, I measure its approach to the critical point.
Right, but we're not dividing by 1, right? What we're doing is all of those are being captured by this scaling relationship. Like it's true that each material will have a different volume fraction phi naught, but it's still captured by your -2 power law, okay? Whereas here, I have a new divergence, and that's captured by this new power law. And so that's all you get from these materials. Like when you do same universality classes in 2 hard materials, the details of the approach are different. Like the values of where the critical point occurs and the coefficients might be different, but the scaling relations are identical. That's what tells you the universality class, and that's what you're checking for in the collapse. So I think it's very similar, exactly the same as what we do in other materials. Okay, that's my understanding. And so there's, in this shear thickening situation, like an underlying physics right, is this crossover scaling from a critical point associated with isotropic frictionless jamming to one associated with shear jamming. And this is the universal sort of picture that we have. But like you say, for each material, there are, of course, going to be details of where phi naught is, of where what your CFI is, right? How does F of sigma depend on sigma star? All those details are, of course, different for each material, okay? Just like they would be for any critical phenomena in hard materials. Yeah. Well, we don't know. I mean, it could be that it's related to things like if you have the normal stress and like some sort of friction that relates the normal stress to the shear, but we don't know. Okay, so I can't tell you that. All right. Okay, so let me keep going and see. Oh, go ahead. No, for dry grains, you do not get shear thickening. You either have a fluid or a jammed state. You could do that in simulations, okay? And you can, I guess you could even do that in a rheometer. So I should correct myself, like Eric Brown did that. But in his rheometer, the way it goes is that those particles are really being fluidized. Like they are, he's shearing the rheometer so hard that the particles are like flying all over the place, okay? But it's really hard to do these in dry grains. It's really hard to do these experiments in dry grains. You cannot get like a lot of these behaviors, these continuous thickening behaviors in dry grains, okay? You really need the fluid in between there to make that happen. All right, yeah. Seems to, yeah. Okay, so what happens? So one way that you could control your suspension is just to alter the particle properties. But what happens if you cannot do that? Like, for example, if you're trying to make chocolate. So in chocolate, there's a process called conching, which you really grind the particles. And that's a shear jamming and stiffening, shear thickening transition that happens. And you definitely don't want to do anything to the particles that the chocolate is made out of, because then the chocolate doesn't taste good and so on and so forth. So one way that we thought about manipulating this transition was to think about applying a biaxial shear protocol. So here's the idea. You flow the particles in a continuous shear so that they shear thicken and form force chains along the maximum compressive axes. And then what you do is you apply orthogonal shear. And by Pythagorean, if you have something that's in contact along this angle, if you start pulling it in the diagonal, you stretch it out. Those frictional interactions will be melted away. Okay, and so the question is, does that work? So the idea, so what Neil did was he took a bidispersed suspension and he put it in a Couette rheometer. You apply a uniform primary shear flow with the outer cup, and then you oscillate the inner bob up and down to create the orthogonal shear. So the outer cup is creating a shear flow in this direction, and the bob is moving it orthogonally. Is it clear? All right, you have an outer cup and then an orthogonal shear. And when we do this, what we set up the primary shear flow so that the system is shear thickened. It's in the thickened state. And then we start increasing the orthogonal shear. And what we find is that initially, the system doesn't do very much at all. So at low frequencies, it just stays thickened. But as we increase the frequency of the orthogonal shear, we can completely de-thicken the system so that it goes back to its de-thickened state. All right? And this works for all of these low, as long as the amplitude is low, this works. If you start increasing the amplitude to the point where you start thickening in the orthogonal direction, then things change. Okay, but basically, the viscosity just de-thickens as long as your amplitude is small. All right, and now again, and just to be clear, you don't need a fancy rheometer to do this. You could take your normal rheometer, like over here, I have a vein geometry. I put my cornstarch in this cup, and what I have is the whole thing is mounted on a speaker. All right, so if I, maybe you can hear, when I turn on the speaker, the system can rotate because I'm orthogonally oscillating and melting away the shear chains. So now it's going fast, even though the stress is the same on the vane tool. But when I turn it off, the system thickens, and now the vane tool has a hard time rotating. Okay, so here it goes again. Vane tool gets thickened. All right, so you can do this at home. Yes. It's not the same because in the gas bubbles, you're really flowing air and releasing all the contacts. Here, we're oscillating it, and we can actually tune the amount that the contacts are loosening, right? Which is what this kind of data shows. Okay, it's less of a step function. You can do the same kind of scaling analysis for this data. So let me quickly show you that, and then I'll finish with telling you how we start to use these. Okay, so the question is, if I have a viscosity versus stress curve, okay, I take one data point there, and I do an orthogonal shear experiment, and I see that I get nothing until over here, and then all of a sudden, it starts to go down. And I can do the same measurement all along this curve, and here are all the data. It's kind of a mess. We can do a little bit better if we realize that it doesn't really matter what the orthogonal shear rate is. It matters what it is relative to the primary shear rate. So I can create a dimensionless parameter, we'll call it capital gamma, that is a function, the ratio of the orthogonal to the primary shear rate. When I do that, all of these data line up. There's a nice knee in the data that tells you where things are going to dethicken. And so this curve gives us all of these data points, okay? We're just doing the orthogonal dethickening for each of these data points along this curve. And I can do that for all of the data sets, okay? So I can do that for all of these different curves. So here is all of that data. All of that data collapses onto the same universal function that I showed you before. Okay, now, instead of just having these parameters, you have to add an additional function, g of gamma dot. That function tells you how the orthogonal shear rate, the dimensionless orthogonal shear rate, controls the frictional interaction. It's almost like the opposite of f of sigma. Instead of turning them on, it turns them off. Okay? So g of sigma essentially moves you up and down that universal curve, right? And again, these are all of that data that I just showed you, right? So we now have a way to manipulate our system and choose where we are as a combination of the stress that we apply, the volume fraction that we have, and the orthogonal shear that we're applying. So far, so good, right? And the fact that you can scale these all into one curve tells you what combination of parameters, to how to combine the parameters in order to get this universal behavior. Yeah.
If you were to increase the shear rate, the viscosity.
Yes?
But now, with these oscillations, if you were to increase the shear rate, you get a different.
No, if you increase the shear rate, it still increases. If you increase the shear rate and increase the oscillations, you could stay at the same point. Increasing the shear rate increases the viscosity, but the oscillations decrease the viscosity. So you could stay at the same point.
Increasing the frequency of the oscillation, sort of like increasing the shear rate.
There's a primary shear rate. That's what we call the shear rate. There's the orthogonal shear rate. That's the orthogonal one. So here what I'm saying is that your sigma is the primary shear stress. That's what's driving you to the thickened state. And what I'm saying is that if you apply orthogonal oscillations, you can now modify that viscosity, okay, and move up and down this curve, okay, just with your gamma dot. Yeah. Yeah, because the amplitudes are all large enough to get the particles out of contact. Okay, so as long as the amplitudes are large enough for that, you're all set. Okay, but not too large to create thickening on the other direction. Good. Okay, so these are the functions now. There are three functions that describe the collapse. Okay, the functions that go into my scaling parameter. Now, you have a new function. Okay, and the fact that this is actually multiplicative is non-trivial. It's lucky in some sense that it just comes out this way. But the idea is that with these three functions, I can now collapse the data set, okay, onto this universal function. And again, I get the same Cardy scaling curve, okay, and the red line here is the fit from the previous data that I showed you. Okay, so again, you get this knee in the data and this -2 power law and this region that has a different universality class associated with it. Okay, yeah. A G of gamma might be, okay? So it might depend on the material. Yes.
So the picture is that's also modifying the fraction of frictional contact.
Yes.
And so gamma is the amplitude of that.
Yes, the dimensionless amplitude. And let me just, yeah, go ahead. I don't think it has to be, but it is. It seems to work. Anna does this, I'll show you in a second, with acoustic perturbations. There it's more complicated. Okay, there's like stress and the voltage that we use are mixed. No, not all viscoelastic materials show this kind of stuff. So viscoelasticity is another beast, right? So if you have polymer systems, you're stretching them out, they can have an elasticity. That's a little bit different from here. We're talking about viscous systems, continuous shear. Okay, they're being torn apart the whole way, right? And this is coming from for shear thickening. Okay, this is what it is for shear thickening, and it's for shear thickening of particulate systems, where there are these two volume fractions that govern the physics. Random loose packing where frictional interactions, and random close packing where there's no space to put the particles in. Okay? So what's nice about this is if I take a look at the phase diagram, what I've done is I've essentially moved the location of my jamming boundary all the way to here. So in other words, if this is my original jamming boundary, here's isotropic frictionless jamming, random close packing, here's random loose packing. If I have a high stress, but I start putting on my orthogonal shear, I can move this boundary all the way down to here, all the way down so it's just to the jamming state, which means that I could set up my system deep inside here, and when I turn those oscillations off, the system would be deep inside the jammed state. You can't see. I would be deep inside the jammed state. I'm moving this boundary from here all the way to here. Okay? And in terms of this RG flow diagram, the idea is that instead of just having your thing depend on this axis depend on sigma and phi, now you can put your gamma dot there, right? And it's all the same. Okay, so I told you that we can do this with orthogonal shear, but that turns out to be cumbersome. In order to do the experiments accurately, you need this dual axis rheometer. But you can also do this with acoustics. So the dream is that you have somebody riding their bike across some pool of cornstarch, and next thing you know, we turn on our sound waves and shake the particles, and the person will start sinking. Okay, so that's the dream. And so we start exploring acoustic activation, and the idea is that nobody actually knows what happens when you send high frequency sound waves through dense suspensions, but the idea is that we think that they scatter through the dense suspension, and if your suspension has a very small roughness, and if the particles repel each other enough, you can, again, melt the frictional interactions. So this is what the apparatus looks like. You have a piezo that's launching these acoustic waves into your suspension, which is in bright yellow. You do your shear, as usual. And what you do is, these are megahertz and hundreds of kilohertz frequencies. And so what you do is you do amplitude modulation in order to modify the acoustic perturbation. And so this is what the system looks like. This is Pratik and Brian Kirby, who collaborated with us on this. And with acoustics, you can also de-thicken the suspension. So here's the viscosity as a function of the acoustic power, and we can get this thing all the way down to the pre-thickened state. And Anna has shown in yet another suspension, these are aluminosilicates, that you can take your viscosity versus shear stress curves, and also the acoustic de-thickening curves, and scale them onto the same universal scaling function. Okay, so once again, we can get all of that scaling. And now I want to talk to you about how we use that to sort of play around with the material now that we understand like the boundaries of the physics. Okay, so how do we create viscosity metamaterials? So the idea is that if you apply acoustic perturbations, the particles essentially scatter the sound and try to repel one another. And when you look at just suspension under glass slides, they seem to want to be hyper-uniform, which means they're not random. They're trying to really be far apart from each other in the most, but they're not crystalline either. All right. And the idea is that shear organizes these particles into these force chains. And so by toggling back and forth between these two states, you can essentially create a metamaterial, and we're going to call that metamaterial a viscosity metamaterial. Okay, so here's how this goes. If I have a system that is thickened, okay, I can apply a continuous perturbation with my acoustics, and that'll de-thicken the system by some amount. If I then toggle the acoustic perturbations on and off, I can oscillate between a thickened state and a de-thickened state, okay, on, off, like this. But now I can do this for different sort of duty cycles, and I can actually generate a system where the difference between the maximum and the minimum of the states can be small. That's what happens in this regime over here. Or I can have a large amplitude difference between the thickened and de-thickened states, right? And I would say that this system has the same average viscosity as this one, but they should be very different materials. Because in one, the structures that you're forming are roughly one size. In the other one, they're oscillating from massive structures to smaller structures. And so, for example, if you have barriers in your flow, one of them might be able to get through, the other one won't. Okay, so they're really different materials. And so in many ways, we're kind of doing what metamaterials in solids do. We're combining small and large sort of features together to create emergent properties that you wouldn't be able to form in natural materials. So let me, again, try to show you an example. So here I'm showing you a stress versus time curve. Okay, so I'm going to apply an oscillatory stress to a suspension, one of my shear thickening suspensions. And if I look at the strain rate for the shear thickening system, it might look something like this. And if I look at the strain, this stress just has a very little offset from zero. So the strain goes from something like here, it increases in this cycle, then it decreases because this stress is going negative, then it increases and decreases, and then maybe you can see a slight difference between this end and this end. Okay, so I move, the net stress is in the right direction, and the fluid moves a little bit, strains a little bit in that direction. But now I can put my acoustic perturbations on, and if I put my acoustic perturbations on when the system is being stressed in the positive direction, I can massively enhance the strain. And so over here, you see that the system has accumulated a large strain over that same number of oscillations. Okay? But I could also do the opposite. I could apply the de-thickening when the system is being stressed in the opposite direction. Okay, and in this case, it gets stuck moving forward, but it's really easy for it to move backward. Okay, and so even though the net stress is positive, this system moves backwards. And that means that you effectively have a negative viscosity. Okay, that's not something that you would see normally in a natural material. Now, of course, we're not violating anything about the second law of thermodynamics. Like at every single point, the system is doing exactly what it's supposed to do. We're essentially doing flow rectification, right, on an oscillating system. So if you were a circuits person, this is just rectification circuits, all right? But if you're a fluid mechanician and you fuzz your eyes and average over many, many oscillations, you get an effective viscosity, which is negative. And that's the philosophy behind metamaterials. You have a medium scale structure, okay, where you fuzz your eyes over larger scales. It looks like a material. That's kind of what Vincenzo does, right? He has a small scale machine that over the large scale looks like a material that behaves with properties that you wouldn't expect from normal solids. Okay, same thing happens here. So depending on that phase, you could get zero viscosity, infinite viscosity, negative viscosity, you get whatever you want. Okay, and the reason why I think it might be useful to define this effective viscosity is that we have a Navier-Stokes equation. We have solutions. And so all you would have to do is plug your effective negative viscosity into the solutions, and you have, everything is done for you, right? You would get what would happen to that flow under the new case. It's a little bit more complicated than that because, It's more complicated than that because, of course, the viscosity depends on the flow, okay? But that's kind of the philosophy of it, okay? There are questions, yes?
Basically very specifically to the
Yeah. That is correct. You have to be a Maxwell demon. Yeah. But there are situations where we can do that. You know, like we are intelligent enough to apply them at the right time. Yeah. But you are absorbing energy. I'm oscillating the system. I'm acoustically pumping energy in the same way that Vincenzo puts in energy at the microscopic building block to violate on the macro scale the, conservation of energy. Same thing happens here. So you're pumping energy in with your acoustics in order to melt the frictional forces. And if you're pumping energy in, then you can generate scenarios where on the macro scale, when you fuzz your eyes, you get a negative viscosity. I'm not violating anything point by point, right? At every single point, right, the flow is the flow, it has a viscosity, I'm putting in the acoustics, there's no violation of the second law of thermodynamics. I'm pumping in energy. So that's what's balancing it. I'm pumping in energy through the acoustics. I don't think you need to do anything to remedy that. That is what you mean. Things are going to blow up. Look, when I do this, right, I can create a system that should not point by point be moving very much at all, but is going to move a lot in the positive direction or a lot in the negative direction. Yeah. Okay, so again, let me come back to Vincenzo's solutions. When his oscillating waves explode, what do we mean there? We mean that the amplitude grows. Okay, so I don't know exactly how this is going to play out here, but the idea is that if you pump energy at the right time, you can resonantly, increase the amplitude of things. That's okay. Nothing wrong with that. Yes. I agree that the situation will be more complicated. I don't know what the answer is, but I think it's at least interesting to think about. Let me do one more example. Yeah.
I mean, I guess you can. So you're saying just solve this equation with the negative viscosity.
I'm not really saying that. I'm just saying philosophically, right? The idea of defining a negative effective viscosity could be useful. We could do something like say, let's just think about like each moment in time and solve the the real Navier-Stokes equations, right, with the shear thickening flows, and then we put in the acoustics and we bootstrap ourselves to what happens to the solution at the macro scale. But I'm suggesting that we may be able to circumvent that, fuzz our eyes, think about a averaged property of the material, and then solve for those solutions. Okay, that's the philosophy here. And I'm sorry if I'm being sloppy in the way that I'm saying it. Yeah.
You worry about higher gradient correction, since now
Perhaps. Perhaps. Yes. Yes. I think you would. There's all sorts of complications that will come into it. We're just at the beginning of trying to think about it this way. Yes.
This equation blows up, but obviously your experiment is not blow up. But what effect kicks in?
I guess I don't understand what you mean by that. Like I could have a stress that's 0, okay, on average, and yet my strain could increase without limit. That's what I see as blowing up. That's a solution that blows up. My stress is 0. My solution still blows up. So I do think it is what I'm saying, okay? And it is an emergent behavior that comes from like manipulating the fluid in this way. I do want to talk about this last part, right? I told you about tuning by pruning. And so the question that I want to ask is, if you have a solid granular suspension or a solid suspension of particles in a fluid, it's actually quite hard to manipulate the solid phase. And so one thing that we've thought about is how do we could we, for example, manipulate the fluid phase and then turn off that manipulation to jam it? In other words, are all these jammed states the same? Like what happens if we acoustically put ourselves inside this regime and then turn off the acoustics so that the system jams? Does that get us somewhere closer to that tuning by pruning idea and allow us to manipulate the properties of the jammed state? Okay, so here's another example. So here's what we're going to do. I'm going to apply a continuous shear like before, and now I'm going to train the system. I could either have no acoustic perturbation, 0 power, or I could train it under some acoustic perturbation for some amount of time. And we're going to see what the difference is in the suspension when we compare those two cases. Okay, so here's the idea. I apply a continuous shear stress. I have different powers of the acoustics that I train the system under. And now I'm going to measure the viscosity as a function of time. If I train at a low power, the system just shear jams. These spikes indicate jamming, okay, in our rheometer. If I train it under 0.25, it's still shear jams. But if I train it at 4 watts, then I get this yellow curve. If I train it at 1 watt, I get this orange curve. 9 watts, I get this green curve. So these are no longer, even though my stress is exactly the same, they no longer shear jam until I turn off my acoustics and boom, all of them shear jam. Okay, so this stress is big enough to shear jam my system. But if I have a high enough power, I can flow the system nevertheless, okay? And what we're going to do is we're going to prepare these states after these different training protocols. They're all in the jammed state. And we're going to do a cessation experiment, and we're going to do a reversal experiment. I'm going to show you what we find. Okay, so here's what happens. You do a shear cessation, which means that you no longer shear the system. The strain rate goes to 0. And when we do that with a system that has not been trained, 0 watts, what we see is the usual. You have a shear thickened state, and then when you turn off the shear, the system relaxes with this exponential relaxation. Okay, so the force chains are melting away with some exponential relaxation time. But if we start applying acoustic training, that time scale changes. And in fact, we can start to get systems that when we turn off the shear stress, increase the stress. Okay, which is totally nuts for anyone who's ever done rheology. Like, what is going on over here, right? Like, how are you increasing the shear stress when you're not applying shear, all right? And the idea that we have is that there are actually multiple directions that force chains can be aligned in, and some of them are aligned along the maximum compressive axis, but some of them are aligned along the maximum extensive axis. And both of those have projections onto the shear stress direction. Okay, so what we think is that you actually have different networks that are relaxing at different rates that are able to give you this kind of relaxation. So effectively what I'm saying is that these networks are playing a little tug of war. There's the primary force chains that are resisting your flow, okay? And then there's the secondary force chains that are aligned in a perpendicular direction along the maximum extensive axis. Those are actually helping your flow, okay? So your total stress is the combination of the primary and the secondary force chains. Okay, they both have a projection onto that shear axis. And so if the secondary force chains relax faster than the primary force chains, you could get a total stress that increases. Of course, later in time, everything will decrease back to 0, and that happens too. Okay, so we see that that increase is not forever. It's hard. Here's my problem. We've tried this. I mean, one of the main things that I did in my career was to build a rheometer that allows us to image things in confocal. Okay, so here's two particles that are exerting a large force on each other. And here are two particles that are exerting a small force on each other. See the problem? It's very hard to tell, right? Like, you can do this there, okay, in 2D. Well, that's hard because I don't know what acoustic perturbations look like for granular materials. And also, I don't know if this is a 2D versus 3D thing. Like, it's a little bit complicated. Also hard, but we've asked people to look for it. So this is brand new results that was just published. Yeah. Yes. When you're going in the forward direction. Let me show you what happens when you do shear reversal. Okay, so if I do a reversal experiment, so now remember in the reversal experiment, in the original ones, we kind of use the reversal experiment to see the contact versus the hydrodynamic interactions. So under normal shear, you form the force chains, you do a reversal, it drops down to the hydrodynamic limit. But what we see is that when we apply acoustic perturbations, you actually end up forming these secondary force chains. So I'm plotting for you here the minimum viscosity as a function of the training power. If I train at 0, okay, I basically go down from the thickened state to the hydrodynamic state. But as I train under higher and higher powers, I don't go down anymore. The minute I reverse, I hit the other force chains that are opposing my flow. All right, so that's another clue that we have the secondary force chains that are preventing the flow. Okay, in reverse. Oh, we don't know. There is an asymmetry. There's an asymmetry between the primary flow direction. So we are applying acoustics while this is flowing. There's an asymmetry. Somehow the acoustics do like organize the particles, and it's easier for them to to relax along this direction than this one. And I don't know why. But there is a symmetry breaking. And one more piece of data here is that the distance that you have to reverse before you get the thickening shrinks to very small, okay, as you increase the training power. So we really think that it's the secondary force chains that are building up when we train the system, okay? They're not building up during training, but somehow the training is setting up the system so that when we turn off the acoustics, it jams with secondary force chains more fully formed. Yes? If you increase the amplitude of the acoustics, you get a de-thickened state. You melt the frictional interactions. So in this experiment where we sheared this way and we did this, for small amplitude, as long as you separated the particles by some little amount, everything de-thickened. If I go too high of an amplitude, it thickens along these directions. Here, I don't know, the acoustics are always small amplitude. The acoustic waves are tiny, tiny amplitudes. So there's something else that's going on in that training, and we actually don't know what it is. But let me kind of give you let me skip this part because we're almost at the end. But let me give you the kind of upshot, which is that, I showed you that just by training a system that's being sheared in this direction, I could independently control the ratio of these two, stress components. But there's nothing that says that I can't do shear along this direction, okay, diagonally, and train these two components, and then that direction, and train those two components, and effectively program in the stress tensor for the resulting jammed state. Like, we don't know anything about how this training is occurring. And in principle, we could start to design the different components of the stress tensor by combining shear and acoustic protocols together to form some sort of new material, okay, with, again, a metamaterial where we design the stress components in the system, okay? And whether we can do that or not, I don't know, but it's another idea, okay, that of the way we're thinking about this system. And I'll leave you with one other really quick idea. So here is an active suspension. This is a dense three-dimensional active suspension, also shear thickening. In this case, I'm applying 0 volts to the system, and particles are static. They're big. Over here, I'm applying 3 megavolts per meter. These form Quincke rotors, and those Quincke rotors look like they phase separate into a kind of gel system. I don't know if this is a spinodal decomposition or what it is, but this is another jammed state, okay? It's not perfectly jammed. You can see little regions here that are reorganizing, okay? But again, you're going to get a thickening transition, okay, from something that, is flowing to something that under shear is going to have a rigidity. And the question is whether or not this whole formalism of crossover scaling, of trying to create metamaterials, is that something that we can also do with activity in these kinds of suspensions? Well, these are moderately to 3D, like 6 or 7 particle diameters, but in the rheometer, they're fully 3D, okay? And I don't have a full story to tell you there, but we're collecting the data, all right? And that's work in collaboration with Eric. Okay, so I'm going to finish by just telling you all of the wonderful people, or showing you all the wonderful people that I've had the pleasure of working on this with. They're all fantastic scientists and engineers. And the latest one is Anna, whose data I showed you as well. And with that, I'll put up the various papers in case you're interested. And thank you for your time. There were a lot of questions, but if there are others, I'm happy to entertain them. Yes.
Yeah. Stress states. It's more just preparing systems with different stress states, right? Not just, I mean, that's a great thing to be able to.
Well, I don't know, because if I can structure the material, if I can structure the jam state, right? If I can like hierarchically structure it, I think then it becomes a metamaterial. So I don't know exactly, like if I have a solid metamaterial, it's solid, right? But it has emergent properties like waves that you can propagate inside or elasticity that are emergent, okay, from the structure. And I don't know how far we can get with these. But I think the idea, like I don't know how to reach into a granular pack and change the bonds. Like I don't know how to tune and prune in a solid system, but I do know how to manipulate a fluid. And this seems to be a powerful way to do it in order to set up some sort of precursor state that upon jamming creates a very different material. And that's interesting.
I mean, I'm a little bit with Andrew here. I'm not sure I'd say it's a different material, but it's a material that's, I mean.
If I test that material in a reversal, or if I do a cessation, it's very different.
Say it's the same material, but it's not an equilibrium system, so it's got a memory of the way it's been treated.
I don't have a problem with that.
But it's the same thing. It's the same material.
No, it's not the same material. It has a different structure.
It's history.
But it's a different structure. So if I tell you that if I 3D print it this way, I have this structure, and I 3D print it that way, I have that structure, it's still the same material under your definition. It's just the memory of how I printed it. But the emergent behavior for these two metamaterials could be very different. So I'd say those are different metamaterials. Even though they're made out of rubber, even though the history that I printed it with is different. Like, yeah, I think if you think about like cold rolling or work hardening,
It comes out a different material.
yeah,
That's what you would say.
yeah. Yeah, so I'm not changing the iron, but I am changing the way that it's structured. I'm changing the defect structure. I'm changing the crystal grains. I'm changing all of that. It's a different material. That's philosophical. I mean, again, I don't care about the words, but that's the idea.
See, materials science and the material science community, I think this example of cold rolling is great because people talk about materials processing as a way to manipulate the material, and then think about different steels that have undergone different processing to have different properties. So I think, yeah, I mean, it's a provocative way of describing it, but I think
That's what I want to be, is provocative.
But I do think there's precedent in the materials for thinking that.
Yeah, I mean, again, like the question of how much control we have in this processing, I don't know. Like, will we be able to really create hierarchy of structures, right? Right now, I just showed you one training protocol, right? I just applied different power for 50 seconds and then we're done. What happens if I start pulsing it? What happens if I, have training periods that are longer and shorter at different powers? Like there's all sorts of things that I can do in this sort of training that could create a very different response at the end. And so I think that's the idea behind the tuning by pruning, right? That flexibility that these random jammed packings give you to really tailor material properties, whether we could do that structurally and, spatially and temporally, like I don't know how far we can get. But that's the idea, and I think it's something that is worth investigating. Thank you.